Hello. In this chapter, we will be focusing on a new electrical component. This component is called an operational amplifier. Operational amplifier. Sometimes it is just called an op-amp. An op-amp is a shorter version of operational amplifier. And we will be analyzing an operational amplifier in this course using ideal scenarios. Ideal meaning perfect. So ideal operational amplifiers. So let's get started with this topic. Let's start talking about operational amplifiers. Operational amplifiers. This is very long. It's a long word. So we just shorten this to call it an op-amp. Op-amp for short. And so what is an op-amp? Well, you can think of an op-amp as just this electrical component where we put in a certain voltage Vn, and then out of it we get V out. So in and out. And between here, what happens is it amplifies the signal. So amplifies means make bigger, amplify. So if we put in a small bit of voltage, on the out, it's going to make it this big. If we make it this big on in, it's going to be much bigger on the out. So it amplifies the signal. So that is why it's called an amplifier. And in between here, our V out is equal to A times V in. And this A can be 1, it could be 2, it could be 3, 4, 5, 6, whatever. It could be very big. It can be a very big number. So it's a way in analog circuits to put in a small voltage and get a much bigger one out. Okay. So we use a specific symbol for an op-amp. So an op-amp we write as it is a triangle. A triangle here. And this op-amp, it can do things like addition, subtraction, multiplication. It has a lot of functions. So here we'll say that this is V out. And V out, and we'll just write a ground here. All right, so V out is between here and here. Furthermore, we have two wires coming in, two inputs going in there. So two inputs going in, and we can call this one V1. Let's call this one V1. And this one V2. So, and let's say that this is plus and minus. So this is our operational amplifier. And usually we have to give it a little bit of power. So we'll also have something like V plus and V minus. And our input, our Vn here, is equal to V2 minus V1. So it takes the difference between those two inputs here to get Vin. And then we have Vout or VO, V naught here, is going to be equal to A times Vin. And so we have this A value is called the gain. It multiplies the signal. So if we want, we can plot what this looks like. So this is our Vin, and this is Vout. And if this gets bigger, we have some sort of linear relationship here. So it goes through 0, something like this. And the slope of this line, the slope here, is equal to A. So we still have this relationship here. Now, depending on our operational amplifier here, Vout must be smaller than V plus, right? So we usually have a saturation is what we call it. So it looks something like this, and this is at V plus, and this is at V minus, because we cannot get more voltage out than we have available there. Okay, so this is an op amp here. In this course, we will be talking about ideal op amps. So to start talking about an ideal amp, an ideal operational amplifier, so we will talk about ideal op amp. And we use this word ideal to mean perfect. Perfect or flawless. Flawless is what we would use ideal, meaning a perfect situation. A perfect situation. And we simplify the op amp. We make it easier through using an ideal op amp. So we will still use a triangle for the op amp here. And it still has two inputs. And so we can say this is V1, or let's say V2 and V1, and this one is Vout. So in this scenario, for the ideal op amp, we have I2 and I1 being the current going in here. So for an ideal op amp, we make several rules. Rule number 1, I1 is equal to I2, which is equal to 0. No current is going into the op amp. No current is going into the op amp at all. Okay. In addition, we say that the gain, remember, the gain is A times the difference between these output. A is approximately infinite. So it is very, very big. Very big. So with that, we say that V1 is equal to V2. So these two are equal. These two are equal. They're equal. Okay, so these two are equal to each other. And sometimes, because they are equal, we will just call it Vs. So the voltage of the source. So Vs. We will just say Vs here. Okay, so those are the basic rules that we will use to analyze op amps. So let's get started on doing a simple example with an op amp. Let's do an example with an ideal op amp. So I'm going to draw a circuit that has an op amp and go plus, minus here, and then we have an output, and this output is connected to a resistor, which is connected to ground, right? Our reference 0 volts. And here we then have a resistor here and another resistor here. And this is connected to one of our inputs. And then the other input is connected to a voltage source here. Okay. And let's label some of these resistors. This is 40 kilo ohms. This resistor here is 20 kilo ohms. And this resistor here is 5 kilo ohms. And we're going to call the voltage here, that is V naught, from here to here. That's V out, if you want to call it that. And this input voltage is Vs. And let's label this voltage here, that is V1. That's this voltage. And V2 is here. Okay. So this is our circuit, and we want to figure out the gain A. We want to find the gain, the amplification, and we want to figure out what is V out when Vs equals 1 volt. Can you see that? Let's make sure you can see that. Yeah, okay. So these are the two things that we're trying to find. And this is an ideal op amp. So let's draw some currents here. So let's call, or I guess we're to find I naught. I'm sorry, I messed that up. We're supposed to find I naught when Vs equals 1 volt. Okay, so let's go ahead and get started by labeling some currents. We'll call this is I naught coming out of the amplifier. We'll call this I2, and this is I1. And because this is an ideal amplifier, the current here, I2 is 0 and I1 is 0. In an ideal operational amplifier, the input current is always 0. So remember that, this is 0. And then we'll call this I3. The current here is I3, and then the current this direction is I4. So we have all the currents labeled. Now let's try to find V1 first. So we need to know what V1 is. Well, V1 is this point here. And if we take a look at the current coming out of the amplifier, the current coming out, it goes this way and this way, right? no current goes into the amplifier. So I1 is 0, right? I1 is 0. So all of the current goes this way. So the 40 kilo ohm and the 5 kilo ohm are in series. These are in series. So to find V1, we can use voltage divider. Voltage divider. So V1 is equal to 5 divided by 40 plus 5 times our V naught. V naught here, or V out. V out. And so that is equal to V naught divided by 9. Now, one more thing about an ideal operational amplifier. We said that V2 is equal to V1. These must be equal, which must be equal to the source here, right? This source voltage. So this is also equal to V naught over 9. So this is equal to this. These two are equal in an ideal operational amplifier. Okay. So how do we figure out the gain? Well, the gain, remember, is the V source times A equals V out. Okay? So if you take a look at this equation, we have this is equal, A is equal to 9. So that is the gain. Remember, we call this the gain. The gain. The gain is 9. So if we put in a small signal, it's going to be multiplied by 9 on the output. So that is the gain. The next thing we want to find is I naught when Vs equals 1 volt. Okay, so the second part here, we want to figure out I naught. And we know that V naught, if Vs equals 1 volt, V naught here is equal to 9 volts. 9 volts. Okay. So let's do KCL right here. KCL, Kirchhoff's current law right here. And so we're going to do in minus out equals 0. And coming in, we have I naught. This current here, I naught. Minus going out is I3 minus I4 equals 0. Now we have I naught. I3, since all the current is here, that is our V out divided by our 45. 45. And I4 is V naught divided by 20. Okay, and remember that we put in 9 here. V out is 9. And so if we do this calculation, I naught comes out to be 9 divided by 45. Nine divided by 20. This comes out to be here. This comes out to be, let's see. Nine divided by 45 plus 9 divided by 20. That is 0.65. And notice that this is in milliamps. This is in milliamps because our resistances here, these are in kilo ohms. So this comes out to be milliamps. So 0.65 milliamps is the current coming out of here if the source voltage is 1 volt. Now let's take a look at a special case using an op-amp. So using an op-amp, we have a special name for this, and it's called an inverting amplifier. Inverting amplifier. And I explained before, an amplifier, the word amplifier just means to make bigger. Make bigger. Inverting means to switch something. So the inverting part can make something from positive and turn it into negative, or it can do negative and turn it into positive. So it can go both ways. So it switches. So inverting amplifier means both to switch and make bigger. Okay, so that's what inverting amplifier means. So I'm going to draw a circuit of an inverting amplifier. So let's start out with a voltage source. We'll call this Vs. And this is connected to a resistor, which then goes into an operational amplifier, an op-amp. And this is negative, positive. And it comes out, this is our V naught. And we'll connect that to ground down here, our reference voltage, ground. So that is here. Okay. Now, with our V naught, with this, we then will use a we'll just connect that straight to ground. Straight to ground here. Okay. And lastly, we put in another resistor up here. And I'm going to label this resistor R1. And this resistor here is RF. The letter F, because this is our feedback resistor. This is called the feedback resistor. So feedback resistor. Feedback resistor. Let's make sure feedback resistor there. Okay. So how does this work? Well, let's label some currents here. So we know that this is 0 amps. 0 amps. Nothing is flowing in here. And the same for this one. This is 0 amps. 0 amps. So nothing is flowing into our ideal op amp. Okay. Now, the voltage, let's label some voltages here. We'll call this V1, and we'll call this V2. V2 here. And we know that this is over here V source. We know that that voltage here is V source. So if we take a look at the currents, let's label the currents up here. We'll call this I1 and I2. So no current is going through here. So let's do our KCL at this point. KCL, and we can do in equals out, in equals out. So we have I1 coming in, and going out, since this is 0, we just have I2 going out. So this is 0, this is I2. So we have I1 equals I2. Well, I1 is equal to Vs minus V1 divided by R1. And that is equal to I2. And I2 is equal to V1 minus V naught over here divided by our feedback resistor. Okay. Now, another thing about the ideal op amp, remember we said V1 is equal to V2. These two are equal to each other here. Well, we know V2 because it's connected to ground here. V2, that is 0. So V1 must be equal to 0. So let's take, we'll set V1 to 0 here and here. And rewriting this equation, we get Vs over R1 is equal to negative V naught over RF. And we can move this over to the other side. We have V naught is equal to negative RF divided by R1 times our voltage source. Okay, so there's a negative sign out here. So what does this do? Well, negative RF divided by R1, this is our gain. So depending on these ratios here, it's going to make it bigger or smaller. It is this ratio that determines it. But then there's a negative sign out front. So it inverts the signal. So if we put in positive, we get out negative. Okay? If we put in negative, we get out positive. So that's what an inverting amplifier does. And this is a quick example of how it works. We just covered the inverting amplifier. Now we will move on to another amplifier, which is called the non-inverting amplifier. So remember, inverting means to switch. Non means not. So this does not change the sign. So if we put in positive, we get positive out. If we put in negative, we get negative out. So this is a non-inverting amplifier. So it makes things bigger, but the sign does not change. Okay, so let's draw this non-inverting amplifier. So we have our op amp here, and with our op amp, then we have our coming out, we have our V naught, our V out here, which was positive, negative, and here we have a voltage source. We can call this Vs, our voltage source, and then we have our other input is then connected to a resistor. Let me draw that again. A resistor that goes then to our ground here, which here's our reference, our ground, and we'll call this R1. And then we still have that feedback resistor, which is here, and this is our feedback. So this is our feedback resistor. So it's slightly different here, and we know we're going to label our voltages. We'll say this here is V2 and this is V1 here. Okay, and we know that this is 0 over here. So let's label the currents, and we'll call this I1 and this as I2. And we know that no current is going in here or here. So there is no current. So this and this, those are 0 here. Those are both 0. So let's solve this. And what we're going to do is a KCL at this point here. Okay, so we have in equals out. So we have I1 is equal to I2. And I1 is equal to this voltage, which is 0. So we have 0 minus V1 here, divided by our resistance R1. And then that is equal to I2, which is V1 minus V0 divided by this feedback here, RF, this feedback resistor. Now in this case, we know that V2 here is equal to Vs, our source voltage here. V2 is equal to Vs, which also is equal to V1. Okay. So if we plug that in, we get 0 minus Vs divided by R1, which is equal to Vs minus V0 divided by Rf. Now let's simplify this a little bit. We can just erase this 0 here. And so we have negative Vs over R1. And then let's bring our Rf to the other side. So we have Rf divided by R1. And we need a negative sign out front. Vs is equal to Vs minus V0 here. And let's move this to this side, the Vs. So we have negative Rf divided by R1, Vs minus Vs equals negative V0. And then lastly, we will multiply both sides by negative 1 here. And we get Vs plus Rf divided by R1 Vs equals V0. And then lastly, we can pull the Vs outside the equation. So we get 1 plus Rf divided by R1 times Vs equals V0. So here is our gain. This is our gain, which is equal to 1 plus Rf divided by R1. So depending on the ratio between RF, our feedback resistor, and our resistor 1, depending on this ratio, we add 1 to it, and that is our gain. That's how much we get out of this. So for example, if RF is 5 and R1 is, let's say 1, then we get 1 plus 5 over 1, and that would come out to be 6. Okay? So that would be the gain here. So we would get 6 times the V naught, what we put in as Vs. Okay? The gain would be 6 if we had RF equals to 5 and R1 equals 1. So that is this here. And this is called a non-inverting amplifier because this is positive. We put in a positive value here and we get a positive value out. If we were to put in a negative value, we would get a negative value out. And that is why we call it a non-inverting amplifier. Now that we've covered both the inverting amplifier and the non-inverting amplifier, let's move on to talk about the summing amplifier. So summing amplifier. So sum, S-U-M, means addition, right? So if you have 1 plus 2 plus 3, and that is equal to 6, we say 6 is the sum of 1, 2, and 3. So sum means to add together. Summing means to add here. So we have a summing amplifier, and I'm going to draw a quick circuit here which has 3 inputs, and they're all connected together. So we'll call this V1, V2, and V3, and this is R1, R2, and R3. And this is then all connected to our op amp, which here, and that is then connected to our ground here. So these are all in relation to our ground. So this is 0 volts here. And there we have our output, which is V naught, V out. And then we have one more resistor here, and that is our feedback resistor, RF. Okay. So since I already have 1, 2, and 3 over here, I'm going to label it a little bit differently. We'll call this voltage VA, and we'll call this voltage VB here. And likewise, let's look at the currents. We know that this current and this current are 0. That's 0 here. So we have all of these currents. We could say that this is I1, this is I2, and this is I3. And when they all combine, that is we'll just call that I. So all of these together combine for I. And I is also going to be here, right? Because all of this flows this way. So I is here. Okay. So let's take a look at what is going on in this summing amplifier. The summing amplifier here. So we know that if we do KCL at this point, I is equal to I1 plus I2 plus I3. All of these together. That is equal to I here. Okay, so we know we also know that I1 is equal to V1 minus VA, because this is the same voltage, VA, divided by R1. And I2 is equal to V2 minus VA divided by R2. So that's this current here, V2 minus this VA. And then lastly, I3 is equal to V3 minus VA divided by R3. Okay. We also know what I is. I here is written as VA minus our V naught over our resistance, our feedback resistance RF. So VA minus V naught divided by this value here. And that is I. Now, if we go through this, since VB is equal to VA, so these two are equal, and we know that VB is connected to ground here, which is 0 volts. So let's go through there, and so VA is 0, VA is 0, VA is 0, and VA is 0. Okay, so rewriting this equation, we have negative V naught over RF is equal to V1 over R1 plus V2 over R2 plus V3 over R3. V3. Okay. So let's simplify this. V naught is then, it is equal then to negative, don't forget the negative sign, so it inverts, and we have RF divided by R1, V1, plus RF divided by R2, V2, plus RF divided by R3, V3. So with this V out here, we can scale each one of the voltages. We can make them bigger or smaller depending on this ratio, RF over the resistance. Okay? RF over the resistance here. So we can make them bigger or smaller based on these ratios. Now let's take a look if we set all of the resistors equal. So for example, if R1 equals R2, which equals R3, which equals RF, all of these are equal. If this case happens here, our V naught, let's write it up here, V naught is equal to negative RF divided by R1. If these are all equal, we just get V1 plus V2 plus V3. So it adds all of these together. So you can think that gets back to why it's called a summing amplifier, because it adds all of our voltages together. But using different resistances, we can scale and make them bigger or smaller, adjust the gain for each one of the voltages, and then add them together. So we looked at the summing amplifier, and now we're going to look at the difference amplifier. Difference amplifier. So difference means subtraction. So we look at the difference between two things, okay? So we say like 6 minus 4 equals 2. 2 is the difference in this equation. 2 is the difference. So we're looking at a difference amplifier. And this gets a little more complicated because we have our op amp, and we are bringing in two different voltage sources. So we'll have one voltage source here, and we'll call that V1, and that is attached to ground. And we'll bring that out V0 here. So that is attached to ground. And then we also have, well, I forgot a resistor here. So we need to make sure we have a resistor there. A resistor. And then here we have, this comes out and there's a resistor to ground. And then in parallel with that, we have a resistor and another voltage source, which we'll call V2. And we'll call this R4, and this is R3, and this is R3. This is R1. And then instead of calling this one RF, we're going to call this one R2 this time. R2. And we're going to label the voltage here, label the voltage here as VA, and the voltage here as VB. VA and VB. And we have these two independent voltage sources here. Let's okay. Let's continue on. So let's do a KCL at this point here, KCL. And we'll call, so the current coming in here, that current is V1 minus VA divided by R1. And the current going out here is VA minus V out, this, divided by R2. So we're just doing KCL on this node here at A. Okay. Now that we have that, we can simplify this if we want. And it gets a little messy. We have V0 is then equal to, let's see, what's that come out to be? V0 is equal to R2 divided by R1 plus 1 VA minus R2 over R1 V1. Okay, so this gets messy, right? We just simplified it for V not there, V out. And now let's take a look at the KCL for B here. So at B, if we do so the current here, the current there is V2 minus VB divided by R3, and then the current going this direction is equal to VB minus 0 down here, divided by R4. Okay. And we can rewrite this one. Let's rewrite this one. Let's see. VB is equal to R4 divided by R3 plus R4 V2. So just solving this equation here for VB, this is what we get. So we have this equation. We have this equation. And we have this equation. And we can combine these two because we know VA is equal to VB. We know that this is equal to VB. And so we can combine these two together. And it gets messier yet. So we have V naught is then equal to R2, 1 plus R1 divided by R2 divided by R1, 1 plus R3 divided by R4, V2 minus R2 minus over R1, V1. Okay? So this gets very complicated here. But I think we can take a look at this and make it simple. We can simplify this. Well, if we do a specific thing where if R2 equals R1 and R3 equals R4. So if we set these equal to each other and we set these equal to each other up here, we set these and these equal to each other, then we can solve this equation, make this equation much easier. And if we do this, you see R2 over R1 is 1. R1 over R2 is 1. R3 over R4 is 1. So let's write this out. So we have V naught equals, so that becomes, this whole value becomes 1. And this value becomes 1. So we have V2 minus V1. So this is where it gets its name. This is the difference part of it. Difference. So it takes the difference between V2 and V1 and it has its output, if this is true. The last amplifier that I want to go through is not actually an amplifier. It is called a voltage follower. Voltage follower. But it uses an operational amplifier here. And we have negative, positive. And we have two inputs. And we bring in a voltage source here to this amplifier, and that is connected to ground, and coming out we have a V out, and then the negative side of this we just bring up and connect here. Okay, and this here is called a voltage follower. And if we take a look and we call this VA, VA is equal to our voltage source VS, and that must be also equal to voltage B here. So voltage B must also be equal to the voltage source. And then if we take that, we see that V naught must equal our voltage source N. Okay, so this this is a special case here of the non-inverting amplifier, where we have no resistors up here at all, and then we can use this to find V0, and these two are equal to each other.